webinar series as part of the Indian Semiconductor mission in the Semiconductor Packaging and Systems Initiative, which is led by Professor Rao Tumala from Georgia Tech University. Professor Madhavan Swaminathan is the Department Head of Electrical Engineering and is the William Leonard Endowed Chair at Penn State University. He also serves as the Director for the Center for Heterogeneous Integration of Microelectronic Systems, which is sponsored by Semiconductor Research Corporation, SRC. Prior to joining Penn State, he was the John Pippin Chair in Microsystems Packaging and Electromagnetics in the School of Electrical and Computer Engineering, professor in EC with a joint appointment in School of Material Science and Engineering, and director of the 3D Systems Packaging Research Center, Georgia Tech University. Prior to Georgia Tech, he was with IBM, working on packaging for supercomputers. He is the author of 550 plus refereed technical publications and hold 31 patents, the primary author and co-editor of 3 books and 5 book chapters, founder and co-founder of 2 startup companies, and founder of the IEEE Conference on Electrical Design of Advanced Packaging and Systems, EDAPS, a premier conference sponsored by the IEEE Electronics Packaging Society. He is a fellow of the IEEE, fellow of National Academy of Inventors, fellow of Asia Pacific Artificial Intelligence Association, and has served as a distinguished lecturer for the IEEE Electromagnetic Compatibility Society. His most recent award includes the 2024 IEEE Rao R. Tumala Electronics Packaging Award, IEEE Technical Field Award for contributions to semiconductor packaging and systems integration technologies that improve the performance, efficiency, and capabilities of electronic systems. Professor Swaminathan received his BE degree in Electronics and Communication from Regional Engineering College, Tiruchirappalli, now NIT Tiruchirappalli, and MS PhD degrees in Electrical Engineering from Syracuse University. Professor Swami, on to you.
Thank you, Professor Datta Gupta. Let me go ahead and share my slides.
Yes, you have the permission to do so.
Okay. Do you see my slides?
Yep.
Yes, we do.
Okay, very good. Let me get my pointer. So thank you once again, Professor Datta Gupta, and thank you, Professor Rao Tumala, for inviting me to participate here. It's my great pleasure to join and give this seminar. So I've spent almost 28 years at Georgia Tech, working very closely with Professor Rao Tumala. In fact, he was my boss at IBM before I joined Georgia Tech. And the last 9 months, I've been at Penn State, serving as the department head. So at Georgia Tech, I served as the director of the 3D Systems Packaging Research Center, which was started by Professor Rao Tumala. And that represents what we call as an engineering research center that was initially supported by the National Science Foundation. So today I thought what I would do is to share with you on this topic shown here, the future of heterogeneous integration for millimeter wave systems. And really, this is ongoing work. So nobody has all of the answers. So it's more on challenges and opportunities and some of the recent results that we have in this area. And when I mention millimeter wave systems, the main focus is going to be on 6G and beyond. So as an outline, I thought maybe I'll start with describing what is heterogeneous integration. The short form is HI here, and why we believe advanced packaging is a key element for enabling HI. And then I'll start talking about the packaging technologies to enable what I call as next G here, that is 6G and beyond. And then some recent results. I think it's a very exciting area. So those of you who want to get into this area, I think there are lots of opportunities here. And the future, the way I see it, and that is really the center that we have started here at Penn State called Chimes. So let me start with a trend in computing. The reason I start with computing is because many years back, going back 30 years, 30 plus years, I joined IBM, where I started learning about packaging. And I had the opportunity to work with a fantastic team there, and along with Professor Rautamala. And the main driver there was computing, as you know, because IBM was focusing on building these supercomputers at that time. And what is interesting is if you look at the trend in computing over many, many years, let's say 30 plus years, we started with the mainframe, moved to the desktop, the laptop, the notepad, the smartphone, and now we want to start embedding a lot of these electronics and computing into robots, using artificial intelligence and things of that nature. Now, if you look at this figure, there are three things that really stand out, and that corresponds to the scaling of systems. Because as you know, the systems have become more and more powerful, but at the same time, we've been able to scale the volume of these systems. And there are three metrics that drive the scaling of systems. One is just the physical size that is obvious over here on the slide. The second is when you scale, the performance actually increases. And one of the metrics we use for performance is the frequency. And the third, which is the most important one in this today's presentation, is the functionality, because you're going to be combining computing with communication and sensing. And almost every single gadget that we're going to be building moving forward is going to contain these three elements and maybe a lot more than this. So if you look at the semiconductor industry, I think we all have to look to Dr. Gordon Moore, who, in my opinion, is the legacy or is the legacy or the driver behind the semiconductor industry. As most of you know, Dr. Gordon Moore was one of the founders of Intel, and he came up with this very famous law called the Moore's Law. And way back in 1965, he had 4 data points that he connected, and he made the prediction that the components per IC will double every year. And today, if you follow the trend that is shown here, the transistors per chip have been doubling every 18 months. And that is because of Moore's law. That's been the main driver behind the semiconductor industry. And in fact, it is more well known than Murphy's law. Now, way back in 2007, he was interviewed as part of the IEEE Spectrum magazine, as shown over here. And when the interviewer asked him, what would you like your legacy to the world to be? He said, anything but Moore's law. Because Dr. Gordon Moore was a scientist and an engineer. Moore's law is an empirical law. Okay, but having said that, that has been the main driver for the semiconductor industry. And today we know that when you try to scale these transistors, the performance actually increases quite a bit. But then you have to think about where are we in terms of Moore's law and what has been the main driver behind Moore's law. And that is purely based on economics, because we know how to make these transistors cheaper and cheaper over the years. And that is what is indicated here. So if you follow this green curve, that represents the cost of the transistor over time. And way back in 1962, the cost of a transistor was $7. And today, if you look at the number of transistors you are able to integrate within a chip and then try to calculate what the cost per transistor is, you're close to maybe a nano dollar or so. So that has been a very powerful driver for the semiconductor industry. But if you look very carefully in 2022, there has been an inflection point here, which means that the cost of the transistor has been going up or is beginning to increase as we begin to scale into advanced technology nodes. And that is because of the capital equipment that is required to build these very tiny transistors and the cost of building these very humongous factories to be able to enable that. And that is where advanced packaging comes in. So there are three reasons why advanced packaging is becoming critical for the continuation of Moore's law. One is if you work with a very large die from an advanced technology node, it's way too expensive. So the thinking here is why not disaggregate them and reaggregate them by connecting them together in a package such that you work with smaller dies, higher yield, lower cost, and that's where packaging can help. The second is that you don't always need the most advanced technology node to be able to build a system. AMD has shown that over and over again to us, where you can combine it with smaller dies from optimized legacy technology nodes to be able to get better functionality. And that reduces the time to design. And the third is this move to heterogeneous integration, where not only do you want to have computing elements from legacy technology nodes and advanced technology nodes connected to each other on the package, you also want to integrate a lot of these components, for example, antennas for millimeter wave, and you also want to combine photonics with electronics to actually make that happen. So what exactly is heterogeneous integration? And this is a slide that I borrowed from a good friend of mine, Professor Dr. John Lau, who is with Unimicron. And the thinking is very simple. So if you want to build a system, instead of integrating everything on a single chip, you try to bring in chips from different foundries that have expertise or that are good at specific kinds of technologies. For example, you might bring in a chip from, let's say, Fab 1 based on a 12-inch wafer using a 7 nanometer process. You combine it with a chip 2 based on a 64 nanometer process, maybe another one based on a 100 nanometer process. You combine it with memory stacks, MEMS, and all of that, including the gallium arsenide chips that you need for millimeter wave communications. And you put them all together and connect them all together on a package. Okay? So we have a heterogeneous integration roadmap, where heterogeneous integration refers to the integration of separately manufactured components into a higher level assembly that in the aggregate provides enhanced functionality and improved operating characteristics. So the key thing is, when you build these chips together, you have to address three elements that I mentioned earlier. The size, you should be able to make it area effective or volume effective. The second is you have to improve the performance. And the third is you have to embed that functionality that you need in that kind of a packaging platform. So with that, let me now get into millimeter wave and put it in the context of heterogeneous integration. So why millimeter wave? I'm sure this audience understands why. So typically when you go to higher frequencies, such as millimeter wave, you get a bigger pie because you get more bandwidth, which means your data rate can increase. The second is, as you go to higher frequencies, you can use beamforming technology, you get the directionality, and therefore you can reduce the interference. The third is, as you know, everything is based on wavelength. You go up in frequency, the wavelength comes down, and therefore you can miniaturize quite a bit. And the fourth is these unique properties for sensing, especially when you want to transmit through the fog, rain, snow, look into depolarization effects, micro Doppler, and things of that nature. Millimeter wave comes in to be very, very useful. So that brings us to the wireless communication. And as we all know, 5G is here. And obviously, we're going to go far beyond that. And that is what is shown here as next G. That is the future. And obviously, the next wave is going to be 6G. And if you look at 6G, the reason why we want to go after that is because there are new applications emerging in areas like augmented reality, virtual reality, teleportation, and others related to e-health. And if you look at the connectivity of the various devices that we need to address for 6G, it increases by 1 order of magnitude compared to 5G, to 10 to the power of 7 devices per kilometer squared that you need to connect together. And of course, you want to be able to support higher data rate of the order of 1 terabit per second with applications like these. And unmanned mobility is going to be a very important thing that we need to look at. And more importantly, this intelligent communication, artificial intelligence kinds of solutions are going to be integrated with a lot of our millimeter wave capability. So the frequency band that is of most interest for 6G is shown here, sub-terahertz in the 100 to 300 gigahertz band. That is basically the G band. Now, as we know, one of the biggest challenges we have in wireless communication is the path loss. And as you go higher up in frequency, there are specific frequencies where the attenuation tends to increase quite a bit. And these peaks, the frequencies at which these peaks occur are frequencies that you want to try and avoid. But in spite of that, you have to address this attenuation that you have over here. So if you look at millimeter wave, you're basically looking at the frequency band from 30 gigahertz to 300 gigahertz. And if you look at 5G millimeter wave, the frequency band that is being targeted is between around 24 to 40 gigahertz. And you also have automotive radar working at 77 gigahertz that also phased array solutions today at 94 gigahertz. So I'm going to go even further than that to upwards of 100 gigahertz to try and understand, what are some of the challenges. And as noted here, to be able to compensate for the path loss and the absorption loss, you need to start working with some new ideas for antennas and RF circuitry. So that brings us to the next G systems, what is shown here as opportunities. So clearly for 6G, you need to get into massive MIMO, trying to get to 1 terabit per second speed. And one of the frequencies that is interesting is 220 gigahertz. The other is the D band at around 140 gigahertz. And one of the things you will notice is that to be able to communicate, you need a huge number of antenna elements indicated here as you begin to scale, let's say from 28 gigahertz 5G to 220 gigahertz, which is 6G. And there are lots of issues that you need to try and address, including things like thermal design, beamforming, trying to address metamaterial-based solutions, array architectures, and of course, advanced packaging. And if you look at these two figures here, you have to be able to scale the number of antenna elements to more than 1,000. And in addition to that, you have to be able to scale that data rate as much as possible to, let's say, 1 terabit per second. The communication distances are typically small, anywhere between 10 to around 100 meters or so, to be able to address the path loss. And clearly, as you can see over here, trying to design those antenna elements is very important for beamforming. And this is where meta surfaces come into play, and to be able to optimize that beam and also be able to point it in the right direction. So that brings us to what is the future, and there is a clear move towards antenna to AI platform. And that is what is illustrated here in the schematic. So clearly for 6G types of communications, you need an antenna array, and this is a very large sized array. And you have to be able to have support beamforming technology along with frequency conversion. And you need to be able to convert it into some kind of a digital kind of a data. And that's where the wideband ADC, the analog to digital converter, comes in. And then you have to do a lot of computing where you're going to combine DSP along with these AI accelerators that represents your physical layer that allows you to do a lot of edge computing. So a lot of these devices or solutions are going to be right at the edge, huge amounts of data that you're going to that you need to gather. So what you need are compact and flexible integration of heterogeneous ICs, enabling end-to-end RF to data interfacing systems, which are of high interest to support emerging commercial as well as defense, communication, and sensing applications, including 6G. What is interesting about the schematic over here is we're going to have multiple teams working on it. Not everybody is going to have expertise in every one of these areas. So you have now a very modular way of going after the solution, where you can have an antenna engineers who can work in this area, who can come up with new solutions that can be combined with other existing solutions that can maybe do the AI part of it and things of that nature. So this kind of an approach, I think, is necessary as we begin to start looking into teams that have specific expertise in some of the blocks that are shown here. So let me start with IC technologies. The SoC designer or the IC designer will immediately say, look, we are going to scale the frequencies, everything becomes super small, we'll integrate everything on the chip. So let us see how that works out, right? Now, if you look at the figure here, this blue line represents half a lambda wavelength in air. And if you look at the y-axis, you have half a lambda provided, as well as the square root of the area of a chip. So basically, it's the side length of a chip that is being used to build the transceivers. X-axis represents your frequency. So all these dots over here represent solutions, state-of-the-art solutions that have been published over some time. Now, if you look at this figure, so I'm going to divide this into two parts. That crossover point is shown over here. To the left, you're looking at solutions anywhere that is less than between 70 to 100 gigahertz. And if you look at the solutions over here, the wavelength tends to be small, and therefore you have your antenna elements become very large, and therefore antenna and package or AIP technology is necessary. Interestingly, when you look to the right of that line, you'll find that these chips are actually becoming quite large because you need to be able to get enough output power from these chips. So you're using multiple stages, let's say for your power amplifier. So the die size is being consumed by the transceiver. And therefore, there is really no space for integrating the antennas. So antenna and package once again becomes necessary. So the bottom line is packaging is going to be very, very critical as we move forward. And this AIP or antenna and package technology becomes an absolutely necessary technology. So let me now switch to another frequency band. We have done some work here, and that's the D band. And this is once again in the 60 range of frequencies. A specific frequency being targeted is 140 gigahertz. Now, let's say that you have two towers that are communicating with each other, separated by a distance of 100 meters. You can do some very simple calculations, and you'll find that the path loss that includes the free and the channel loss will turn out to be 133 dB, very large. Similarly, look at scenarios where you're trying to communicate between, let's say, a wireless hub like a transmitter array to the handsets that are shown over here. So based on this, you can create a link budget that, let's say, allows you to communicate between the transmitter on this side and the receiver on this side, separated by a distance of 100 meters. So you have three distinct blocks over here: the antenna, the package, and the radio itself, and something similar on the right-hand side, except the transmitter is replaced by the receiver. So based on the link margin, let's say of 11 dB, you can come up with these numbers, populate numbers on this figure over here. So let me go through this very quickly. So let us say that you have a PSAT for your transmitter of around 37 dBm. So that's the output power. So this radio is integrated in a package. And let us say that you have a loss of 1 dB, right, in the package. And then you're trying to boost that antenna gain as much as possible to be able to get an EIRP of around 72 dBm. Let's say the antenna gain is around, gets you to, has a gain of around 36 dBm. And then you're transmitting that information. There is a loss of 133 dB. Then you recover the signal using this antenna gain. You incur a package loss. You then get to the radio, which has a noise figure, let's say, of 8 dB, and you have an output power over here. So if you look at these numbers, they were all created based on getting a link margin of around 11 dB for, let's say, 128 QAM kinds of applications with a signal interference noise ratio of around 30 dB with a bandwidth of around 8 gigahertz. Now, if you look at this, at these numbers, and ask yourself, what are the challenges? There are three main challenges that show up. The first is your ability to get that antenna gain, and that is where antenna and package technology comes in. The second is to be able to get to that package loss of 1 dB. Most of the solutions today have losses upwards of 5 dB at these frequencies. As you know, with just a 3 dB loss, you're losing 50% of that power from the PA to the antenna array. So you're losing half the power before the energy gets radiated out. And the third is the heat removal, because these kinds of power amplifiers at these frequencies are notorious for generating a huge amount of heat because their efficiencies are low. So you're looking at heat fluxes similar to what you see for CPUs today, 150 watts per centimeter squared. So how do you go about doing this? So that's where enabling connectivity at sub-terahertz frequencies comes in. So you have to develop a technology that can support a scalable antenna array. That's your antenna and package technology. As we know, as you begin to scale frequencies and with this lambda over 2 separation between these antenna elements to keep your side lobes to a minimum, the spacing between these elements is constantly coming down. And therefore, there is hardly any space between these antenna elements to be able to support your feed networks. The second is your ability to make sure that most of the power output from the power amplifier gets to that antenna. And that requires ultra low loss between PA output and antenna array. And that requires you to create a vertical stack like this, where these chips are embedded right beneath that antenna array. And the third is keeping these chips cool. You need an efficient heat removal. So you want to come up with a stack that looks like this, where you have chips that are embedded right beneath that antenna array with phase shifters over here and other kinds of passive components. Where on the bottom side, you can attach your neuromorphic IC to do your AI, and all of this gets assembled onto a printed circuit. So what is that packaging landscape? So there are several technologies already available. One is the ceramic LTCC, low temperature co-fired ceramic technology. To this day, Kyocera makes use of it. It's a very old technology, provides very bulky solutions. The second is a low loss laminate solution that came out from IBM. This is an example for their 94 gigahertz phased array solution. And as you can see, you end up with many layers in that stack that increases your losses quite a bit. The third is this fan-out wafer level packaging originated by Infineon, today being practiced by TSMC. They have solutions at 60 gigahertz. So what we've been doing at Georgia Tech before I moved to Penn State is to focus on glass substrates. And that is work that is being continued through Penn State as well. And we call this as the glass panel fan-out. So let me sort of share with you why this is so important. Now, all of us, including myself, we look to IC technologies for integration. And when you think about ICs, the first thing that comes to your mind is silicon. And silicon has some very nice properties that are shown over here. The surface roughness is very low. The CT is matched to silicon. The Young's modulus is quite high, so it's a very stiff kind of a material you can work with. The moisture absorption, it's an inorganic material, 0%, and the thermal conductivity is quite high at around 148 watts per meter Kelvin, which means you can spread the heat out. But at the same time, with silicon, you have some challenges. And one of the challenges that we have is this package size. You have to limit yourself to the reticle size that you're making use of for the semiconductor equipment. And the panel size or the wafer size is typically around 300 millimeters. Now, there are opportunities to try and work with materials other than silicon that gives you performance much better than silicon. And people have tried out these organic based technologies, and a lot of these solutions have worked very well for frequencies, let's say less than around 100 gigahertz. Now, what I would like to share with you is some new work that is going on by using glass. And if you look at glass and compare it with silicon, you have some properties that are very similar, but there are other properties that are quite different. So one of it is the CTE, which means that you can tailor the CTE of glass such that you can maximize the reliability at the chip interface as well as the package interface. Okay, that reliability CTE of around 7 over glass can help you quite a bit. The second is this thermal conductivity. Glass is a thermal insulator, unlike silicon, which is a semiconductor. So since it's a thermal insulator, you can now embed chips in glass without having thermal coupling between these chips. And then finally, if you look at the package size, you can go to very large package sizes because the size of the substrates or panels that you can work with can be very large, and that increases the cost effectiveness. In addition to that, glass is a dielectric insulating material as opposed to a semiconducting material if you look at CMOS grade silicon, and that improves the performance as well. So this is what we have been trying to do. So let's say that we want to build this 8x8 antenna array module that works in G-band. So you have the 8 channels, each one is a 1x8 antenna array, a series connected, and you connect each one of these elements, let's say, to the PA chip and the CMOS beamformer. So you can take this kind of a system schematic and convert it into a cross section that looks like this. So you can start with glass, right? Similar to what is shown here, create cavities in glass, and then you embed the chip in it. Then you deposit your dielectric layers. When you deposit that, the dielectric layer flows between the chip and the glass, holds the chip in place. Then you pattern it, you plate it, and then you build multiple layers, right? And what is nice is if you look at this carrier tape over here at the bottom, you can now flip it, attach another carrier tape at the top, remove this tape, and you can continue the buildup. So you can come up with a double-sided kind of a solution, and that helps you to come up with solutions like these. So if you look at what is shown over here, you can embed chips of different thicknesses and different sizes inside of these cavities. You can build your phased array at the top. These are all your phase shifters and other passive components. On the bottom side, you can expose the chip, attach, let's say, a thermal interface material, connect a heat spreader to it, and remove the heat from the bottom side. So let me show you some recent results. And so this is an example of this transmit antenna array in the package, okay, in D-band, so 140 gigahertz. And if you look at the build-up here, we work with 200 micron thick glass. These RDL layers, the dielectric layers are polymers. This comes from a company called Ajinomoto, and the glass comes from a company called AGC in Japan. Both of them are Japanese companies. And then we create this. And one of the nice things about these materials is that you can use different thicknesses. We can go down to thicknesses of the order of 5 microns or below and go up to thicknesses of 100 microns or above. So as we all know, when we build these antenna elements, you need to have enough thickness over here to be able to do not only your impedance matching, but also to make sure that you have enough antenna efficiency. And we are able to address that, including integrating the ground plane over here so that you can shield all the chips from here from interfering with these antenna elements. And what you show in the table is a comparison of a glass-based technology over here compared to what has been done with LTCC, PTFE, and LCP, liquid crystalline polymer material, measured bandwidth of around 7 gigahertz, gain of around 14 dBi, and this becomes the building block for a hybrid beamformer that I'm going to show you later. Now, if you look at the antennas you need to integrate into the handset, and as you know, one of the things you need to do is to integrate it in such a way that you're able to communicate with that wireless hub. So that means that you have to be able to integrate these antennas around this handset, and this is where end-fire antennas come in very handy. So this is an example of a linear array, so 1x4 array. This is a monopole antenna with the director here, and it's a single-ended feed because it's a monopole antenna with the ground plane acting as the reflector. So the direction of the beam is basically this way. So you would integrate it into this stack up that is shown over here, right at the top. And if you look at these kinds of antennas, these are actually measured results. it gives you a bandwidth of around 60 gigahertz. The entire D band, a very nice radiation pattern. And you see in this table the comparison of this monopole quasi-Yagi antenna array with what else has been demonstrated so far. So we get some significant advantages in terms of size as well as the peak gain. We've also been able to build other types of antennas. There's an example of a Vivaldi antenna array in the package. As you know, with these kinds of solutions, you get more gain. And what is interesting here is, if you look at the feed network here, this is all constructed using substrate integrated waveguides. And that goes directly through glass. I'll show you some examples of that. So once again, you see how tiny these solutions are, and also the comparison with the state of the art when it comes to, let's say, LTCC and liquid crystalline polymer technologies. Now, when you try to integrate these antenna elements, obviously you need a way by which you can accommodate feed networks. And what I show here are 5 ways by which you can create those feed networks, as well as be able to build passive components. So once again, if you look at the cross section here, this is glass. We're embedding ICs here, and these are those interconnect layers. So we can integrate, of course, the coplanar waveguides and the microstrip lines that all of us are familiar with, that can also be used to create these passive components. We can also build these substrate integrated waveguides, and I'll show you how that is done. You can also create these wireless interconnects, where instead of making use of these vias that connect the top layer to the bottom layer, we can just capacitively communicate between the top and the bottom, right? So that's a type of wireless communication. And of course, these planar gobo lines that allows us to communicate over longer distance. So with these CPW and microstrip lines, our loss is anywhere between 0.17 to 0.33 dB per millimeter. This is at 140 gigahertz. Substrate integrated waveguide, so all it is copper on 2 sides of glass with vias connecting the top to the bottom to create this via fence over here. So here we have an SIW loss anywhere between 0.3 to 0.7 dB per millimeter. The wireless interconnects are these capacitive coupling between the top to the bottom without the need for vias at a loss of around 1.8 dB. The planar gobo lines are nothing but microstrip lines without a ground plane. And so we rely on these surface waves as a way to do the communication. And they get you a loss of around 0.34 dB per millimeter. And of course, these are examples of filters that we've been able to build that gives you very nice bandpass characteristics with very high quality factor and a very low insertion loss. And these are all published information that you can find in the literature. Now, the substrate integrated waveguides to us is very interesting, because one way by which you can create that is to create those via fence that I mentioned. We can also create these trench sidewalls. That means that we can plate metal along the entire edge, and that improves the insertion loss. You can also create these slots in that substrate integrated waveguide to be able to build your filters. So this is an example of a filter that a bandpass filter that we've demonstrated over here, along with comparison with other technologies at these frequencies. And as you can see, the size can become very, very small, and you have very low insertion loss compared to other solutions that are out there. We can also introduce air. So as we know, air is the best dielectric for a lot of the millimeter wave solutions, but it's also the worst dielectric to use when it comes to reliability. So you need to be very careful how you integrate air as part of your solution. So instead of integrating air into the glass, we integrate it into the polymeric layers. So there's an example of a material that we call as Astra. It is from a company called Isola. And what we do is we've created a process that allows you to integrate these air pockets. And you can use that as part of your substrate integrated waveguides or other types of solutions. So as you can see over here, you can cut that loss almost by in half when you try to use these air-filled types of SIWs. Now, how do you bring the chips in? And this is where assembly comes in. So as we all know, to be able to connect a chip to your substrate, you can use a wire bond or you can use flip chip, right? And you'll find that as you go to millimeter wave frequencies, even a tenth of a dB of a loss becomes very, very challenging. So what we do here is just eliminate assembly altogether. So think of glass that I showed you before, where the chips are embedded, where the pads of the chip are exposed, and we build the layers. We just continue the metal layers by connecting to those pads. So there is really no physical assembly. So we just pick and place the chip in the cavity and continue the build-up that way. And when you do that, you see over here with this kind of an approach, the amount of loss that you get tends to be very, very small, around 0.4 dB at 140 gigahertz. And that is, these are actual measurements. So what you can do is to reduce, it's around 0.15 dB lower than a flip chip solution and more, around 1.65 dB lower than the wire bond. So now you have to bring these chips together along with the antenna elements. So that is what is shown over here. So the transition between the chip that you're embedding and the antenna that you're connecting to becomes very critical. So what you want to do is to make sure that the gain of the antenna doesn't suffer when you try to embed the chip and connect it to these antenna elements. And you also want to make sure that the matching at this interface is very good to make sure that most of the power that comes out of, let's say, this PA chip, it gets into that antenna. So what is shown over here are two solutions. One is without the chip, and the second is with the chip. There's a very simple CPW chip, RF CPW die, and this is actually the world's first embedded die with the integrated antenna and the glass interposer in D-band. And as you can see, without the embedded die, we are getting around 11.6 dB. And with the die, it goes to around 10.7 dB. So we are seeing a 1 dB difference that is coming from that embedded die and the transition. So clearly that needs to be improved. So you need to spend a huge amount of time trying to design what the transition looks like. And as you can see, the setup becomes very, very challenging when you make a lot of these measurements. Now, more recently, what we've been able to do is to embed these indium phosphide PA chips. So once again, we work with glass. The thickness of the glass is 100 microns, not 200, right? The thickness of the die is between 75 to 90 microns. And we take this die, we embed it into this glass package, and then we have these dielectric layers on either side that encapsulates the die. That's what is shown over here. This is the bare indium phosphide die at 140 gigahertz. You embed it. This is the packaged part. And you can see, this material is translucent, so you can actually see through that dielectric material. And the die is here. These are all the RDL layers on the top. So this is where you would build your antenna array, right? And if you compare it with what Kyocera has been able to do with their LTCC technology, you get an idea as to the kinds of wire bonds that they're making use of. So this is a more elegant solution. And what we've been able to show is that in a clean room in a university, that we're able to develop a repeatable process. Okay, so these are 3 dies that have been packaged, showing 100% yield, and you see the gain is basically repeatable for multiple chips. Now, coming to thermal, how do you get the heat out? And this is where the bottom side of the chip needs to be exposed. For these kinds of heat fluxes, thermal vias are no good. Okay, so you have to find a way to be able to attach a heat spreader to the backside of the chip as closely as you can. And in this particular case, we introduce a thermal interface material here from a company called Namex that has a very high thermal conductivity and attach a heat spreader to it. So you see the actual chip. There's an example. This is a thermal test chip where we are able to control the heat flux. These are basically thermal heaters. And you see the measurement setup over here. We are pulling the heat from the bottom side, and we are trying to bias these resistors to be able to generate the heat. And these are the actual results. So one of the requirements is that the temperature differential between the ambient and the surface of that chip has to be 25 degrees centigrade. Okay, no more than 25 degrees centigrade. So the x-axis represents the power density of the chip in watts per millimeter squared. Y-axis represents the temperature of the chip. This dashed line represents that ambient plus 25 degrees centigrade. The various curves over here represents your heat, your airflow rate, the convection, right, coefficient. And as you can see, with air cooling alone by attaching a heat spreader, we probably can get to around 60 watts per centimeter squared, push it a little bit higher, maybe to 80 watts per centimeter squared, maybe push it higher by increasing this even more, maybe 100 watts per centimeter squared. Beyond that, you need a different type of a solution. And this is where looking into things like vapor chambers and cool plates come in terms of coming up with some good thermal solutions. So with that, let me try to put the pieces together. So how do you build these antenna arrays? This is where hybrid beamforming comes in. So what you want to do is to take this large array, break it up into subtiles. So let us say that each subtile has a 2 by 2 subarray, and you embed some phase shifters beneath it. So that would, for example, be the Butler matrix. And beneath that, you would embed your chips like your power amplifier and your beamformer. And then you replicate it to be able to build your antenna array. And by doing that, what you can do is rely on these phase shifters to tilt the beam, and then rely on your beamformer to scan the beam over this angle here. So this is a simulation at this point in time that we are trying to implement. And as you can see, you can get to 256 patches. So depending on the gain, you decide how many of these elements you actually want to integrate. And you see where the main lobe is, but you also pick up these side lobes, and that's why beamforming becomes very critical. Now, how do you design all of these? And this is where we believe machine learning can come in very, very handy. And I want to just share with you one example of it. So when it comes to machine learning, one of the areas we are working on is what we call as Bayesian active learning. And what that allows you to do is not only to build these very predictive models, but also use that for optimization quite a bit. And it allows you to take a very hard problem where you're trying to rely on 3D EM simulators to do a design, and transforms it into a series of easier problems that you can work with. And that is the concept that is shown over here. So the model that we create using this Bayesian active learning is called a Bayesian model that can be used, let's say, for optimizing the parameters, but also gives you the predictive capability we are looking for. So if you look at Bayesian optimization, what we do is it's a statistical way of trying to address the problem, where we build this surrogate model that is the mean, which also provides a variance around it. So some kind of a confidence bound that we can use to intelligently sample the design space to be able to come up with good solutions. And that is where these acquisitions functions come in. So the way we pose the problem is we want to minimize the number of times we run this 3D solver to do design. So we minimize the time associated with it because it tends to be very expensive, and instead rely on a machine learning based solution to actually make that happen. So we have applied it to this beamforming for 6G communications. So this is an example of that 2 by 2 antenna array with the Butler matrix beneath it. So this represents your Butler matrix. And what we are trying to do over here is to look at these various parameters here and try to optimize them in a very sort of in a way that minimizes the number of times you invoke that 3D solver to be able to come up with that optimized solution. And the results are shown over here. So if you look at this figure here, this represents your peak gain, your antenna pattern. So the power output from the antenna. And you see, if you look at this purple curve here and compare it with the green curve, which is the original design, you get a big advantage in terms of improving the power that comes out of that antenna. And one of the nice things with these machine learning based approaches is that the convergence is extremely fast. So very quickly, we converge to the region in the design space where we have the optimum solution and then converge to the optimum solution itself. Okay. So, so now the question is, how do you bring the neuromorphic IC in? That is this part over here, right? And the only way you can bring that in is by assembling it using some kind of a flip chip technique, because the heat flux here is very, very large. So you need to bring that out from the bottom side by attaching a heat sink. So this is an example of some recent test vehicles that we built, where we made measurements where we were able to show that this communication speed or data rate between this embedded IC and let's say that neuromorphic IC can be as high as around 17 gigabits per second uh, per IO, which translates to around 9.25 terabits per second per millimeter squared. And the reason for that is very simple. We keep these interconnect lengths as short as possible to be able to create that connectivity. And today, the state of the art, I'm very proud to say, this is work that was done at Georgia Tech, which was all initiated by Professor Rao Tumala, is we have an eight metal layer process for glass substrates. So we start with a glass core, 4 metal layers on either side with line dimensions going down to 2 microns. We can integrate different types of dimensions into that stack up. And this is the first demonstration of such a build-up kind of a technology on glass that has been demonstrated so far, with very fine lines shown here as well as very tiny vias that allows you to connect the various layers together. So with that, let me try to come to the end of the presentation. So what next? And this is where the future comes in, right? And so what we have initiated at Penn State is a fairly large center called CHIMES. CHIMES stands for the Center for Heterogeneous Integration of Microelectronic Systems. It's all about advanced packaging, supported through SRC, Semiconductor Research Corporation, through their joint university microelectronics program. And Penn State is the lead. There are 15 universities total, not 14. And you see there are 15 companies supporting us, funding us, along with DARPA at at around $50 million over 5 years. So it's a fairly large center. So how does this relate to what the topic of the seminar is? So what we are looking into over the next 10 years is this ultra-dense heterogeneous integration platform. And if you look at this package here, we have all kinds of components and chips embedded in it, along with this 3D stack that is shown over here. And there are a total of 7 areas that we have identified, where one of them is that millimeter wave, trying to get to very, very high frequencies, where RF, electronic, and photonic integration becomes very, very important to be able to build these very massive 2D arrays. And that brings us to this 10-year metric versus state of the art. So the metrics and drivers are on the wireless IC side, basically cognition, looking into harsh environments, communications, and things of that nature. The SOTA, the state of the art, is what I just showed you, right? And if you look at some of the commercial solutions, as I mentioned earlier, the insertion loss is actually greater than 5 dB in D-band. And that means that more than 50% of that power, 3 dB is 50% of the power. Huge amount of power is being wasted. And we are trying to address that by getting to insertion losses less than 1 dB, antenna efficiency is greater than 90% at high frequencies to be able to support this signal to noise ratio of around 30 dB. And the solution that we're thinking about is shown over here. So this is the stack that we are trying to build with embedded ICs okay, as well as ICs that you can assemble at the bottom, but more importantly, an heterogeneous stack up of different types of materials, thermal insulating as well as thermal conducting materials, including things like gallium nitride, to be able to handle the power management side of things, to be able to implement future solutions. And there are a lot of details at this website, www.chimes.psu.edu. With that, let me stop here. Thank you so much for listening. And if you have any questions, I'll be very, very happy to answer. Thank you so much.
Thank you, Professor Swaminathan, for that wonderful lecture. It was extremely educational for all of us who have been perhaps working at different aspects, but to see the whole picture, so as to speak. I will request the audience whatever questions they have. So we have a very good audience tonight. So it was crossing 100 at points. And we will request you to put your questions in the chat box. We will capture all of them, share it with Professor Swaminathan, and give you the feedback as soon as it is possible. So I would like to give the microphone to Professor Rao. Professor Rao, would you like to make some comments? Professor Rao? Perhaps I will. Yeah, Professor Rao, please go ahead.
Yeah, okay. Thank you very much, Swami. This is a fantastic seminar, probably the best ever. It's also most attended by by more people than any seminar so far. Okay, and you have given a fantastic overview. Okay, the basic elements that make up 6G and future systems. So India is very much interested in all these technologies. And so working very hard trying to learn from the global experts like yourself in India, okay, where are we today in the areas of the industry's need, looking ahead, and what should India do as an R&D program, looking okay as towards next generation. So clearly, this constitutes the foundation of all of that. So this is the fantastic contribution, Swami, and I hope we can count on you for additional collaborations, discussions, and perhaps tutorials.
Absolutely, Rao. Thank you so much. Thank you for inviting me here. And thank you, Professor Dattagupta, for inviting me as well. So
just so everybody is aware of, okay, the ISM, primarily at the minister's level, based on my recommendation, the 3 major universities in US have been chosen to play a key role in working with the Indian R&D community. They are Penn State. Okay, Professor Swami heads up that. And next is Purdue. Purdue actually signed MOU. So Swami, we can also sign an MOU if you like.
sure.
Okay, from Penn State. Okay, not individual IITs, rather collectively through ISM. So I can help with. We'd like to see that.
Sure.
And the third university is Georgia Tech. So we're looking for many collaborative partners from each of these, as well as some selective collaborators from outside these 3 major universities, where there's particularly special expertise in some areas of India's need. So we're looking for a total of about 24 global experts, 18 of them coming from these 3 major universities and 6 from others. So you can expect to see Professor Swami and his group of packaging experts. I would call them system experts. Okay, really everything Swami talked about in Mavi is all about system. That's the culture we're trying to bring into to India. So don't think of a device, don't think of a package. Okay, those days are gone. It's all about integrating. As Swami touched upon the benefits of integration with systems focus. Okay, that is the highest value add. Okay, and Professor Swami talked about a variety of things we can integrate Okay, integration leads to size, performance, cost, and reliabilities. So that's the point he made. That's true in almost every system. So therefore, the focus in India needs to be, okay, integration towards systems, as opposed to taking discrete elements and components and trying to form a system, okay, that we've been doing for the last 40, 50 years. So thank you. Thank you again, Swami. Thank you very much, Sid, for making this happen.
So thanks very much, Professor Swami, again from our side, and we will continue to pester you with requests for advice. So you cannot deny us.
Looking forward to it. Looking
Yes,
forward to working with all of you. Thank you so much.
Yes. So with that, I'd like to also thank the audience for showing up, and we all can give a metaphorical clap at what Professor Swami has achieved. And of course, also we have to say that Professor Rao has been a major influence there. So, and we are very, very fortunate that all of us are here to help us lead from the front. Thanks very much. Thank you very much.
Thank you all.
Yeah.
Thank you. Take care.
Bye.
Bye-bye. Thank you.
Bye-bye.
Bye. Bye.